Hello, in this video we see the solution to the work example 3, which is on quadratic and cubic functions. So the first exercise is the graph of the quadratic function g of x equal to minus x to the power of 2 plus 5x minus 4 concave up or concave down? And test this by finding the second derivative of this quadratic function. So we have the quadratic function g of x. It's a quadratic function because it has a quadratic term, which is in this case minus x to the power of 2. So we know that quadratic functions can be written in a general form in this way, with the coefficients a, b, and c. In this case, our function g of x has an a coefficient which is equal to minus 1 because we have the term minus x to the power of 2. And since the coefficient a is negative, we know that this means that this function is concave down. But we can test this using the second derivative of the function. Well, if we want to compute the second derivative, first we have to compute the first derivative. And so the first derivative of this function is g first of x is equal to minus 2x plus 5. And the second derivative is the derivative of the function g, in this case is equal to minus 2, which is a negative number. And so we have the confirmation that the curve is concave down because the points where the second derivative is negative have a down concavity. And so we finish the first exercise. The second exercise is sketch the function g of x, which is equal to minus x to the power of 2 plus 5x minus 4. Since we have to sketch, well, the first thing that we have to do is to draw our Cartesian plane. And then we need to remember that to sketch a quadratic function, we need to know the x and y intercepts, which are the points where the function meets the x and y axis, and the stationary point, which is the point where the first derivative of the function g is equal to 0. So let's start with the x-intercepts, which are the points where y is equal to 0. So what do? We take our function and we write it equal to 0. This is a second order equation, and to solve it we need a formula, which is this one. This formula where a, b, c are the coefficients in the second order equation. So in our specific case we have that a is equal to minus 1, b is equal to 5, and c is equal to minus 4. So if we substitute the numbers to the letters, we get that x is equal to minus 5 plus minus the square root of 25 minus 16, all divided by minus 2. This is equal to minus 5 plus minus 3. 3 comes from the square root of 9, all divided by minus 2. And these are two solutions, one with the plus and one with the minus. So the first solution is with the plus, so minus 5, is with the minus, so minus 5 minus 3 is minus 8, which divided by minus 2 is equal to plus 4. And the second solution is minus 5 plus 3, which is minus 2, divided by minus 2 is x equal to 1. So we have the 2 points where the function intercepts the x-axis, and these are the 2 points here. So the function has to pass through these points that we have just written in the Cartesian plane. Now, second step, let's find the y-intercepts, so the points where the x is equal to 0. So we just take our function, substitute 0 where we have an x, and we get that y is equal to minus 4. This was easy. And so we draw the point x equals 0, y equals minus 4 in our Cartesian plane, and this is the point. The next step is to find the stationary point, which is the point where the first derivative is equal to 0. So we compute the first derivative, which is in this case equal to minus 2x plus 5, and then we write that this derivative has to be equal to 0. This means that minus 2x has to be equal to minus 5, which means that x is equal to 5 divided by 2, which is 2.5. Now this is the x value, but we have also to find the y value. And to find the y value, we need to compute the function g at the point 5 half. And so we compute this point by substituting the value 5 half in the expression of the function every time we find an x. And what we find is that the value of y is equal to 9 divided by 4. So the point is this point here, is the point x equal to 5 divided by 2 and y equal to 9 divided by 4. The stationary point is also the vertex of the quadratic function. And so now we can draw our function, which is passing through the 4 points that we have found, and this is the green line. The exercise has a second question, which is, if the function g that we have just drawn in green is the derivative of a function h, what is a possible graph of h? Okay, so we don't have any information on h. We just know that its derivative is the function g, and the function g is a quadratic function. So if the derivative is a quadratic function, it means that the function h is a cubic function, right? In fact, a cubic function is equal to ax to the power of 3 plus bx to the power of 2 plus cx plus d in its general form. And this means that its derivative will be a quadratic function, which is our g of x. And then we have also an additional information. So now we know that the function h is a cubic function, but we also know that the derivative of this function, the first derivative, is the function g, and the coefficient of the quadratic term is negative. So this means if we want to get the first term to be negative, so the coefficient of the quadratic term to be negative, a has to be negative 2. And so we know that a cubic function where a is negative has the first part of the function that is decreasing. And so we can draw a generic cubic function where a is negative. And this is a possible solution. We cannot draw the very specific h function because we don't have any additional information on h. Now we have another work example, the work example 3.2, which is find the second derivative of the function f. This time the function f is x to the power of 3 minus 3x to the power of 2 minus 24x plus 8. Using the a value and the second derivative, we need to indicate where f will be concave up and down, and where is the point of inflection. Okay, so let's start from our function. We need to compute the first derivative, and the first derivative is this function, 3x to the power of 2 minus 6x minus 24. And then we compute the second derivative, which is 6x minus 6. So now we know that this is the second derivative. We know that the point of inflection is the point where the second derivative is equal to 0. So we take the second derivative and write it equal to 0. And we solve it, which means we find the value of x. And in this case, we have 6x equal to 6, which means x equal to 1. And this is our point of inflection. Then we take again our second derivative, and we know that the function is concave up when the second derivative is positive. So we write the second derivative larger than 0, and we solve this exercise, and we find that the second derivative is larger than 0 every time that x is larger than 1. And this is where the function will have an up concavity. Then again, we write our second derivative. We remember that the function is concave down when the second derivative is negative, and so we write our second derivative smaller than 0. We solve this and we find that 6x has to be smaller than 6, and this means that x has to be smaller than 1. And for all these points, x smaller than 1, the function will be concave down. So to summarize, the function f is concave up for x larger than 1, concave down for x smaller than 1, and has a point of inflection in x equal 1. And this is the end of the exercise.